Hello, everyone. Welcome to another talk from Understanding Deep Learning. We are Data, an extracurricular group from the University of São Paulo in Brazil, focused on promoting data science and machine learning to the public of our university and beyond. The goal of our event is to gather advanced researchers from all around the country and the world to present relevant topics in deep learning research to understand what the state of the art currently looks like and strengthen our collaboration networks. And today, we are very honored to welcome Petar Veličković as a speaker. He is a senior researcher at Google DeepMind and also an associate professor at the University of Cambridge. He obtained his bachelor's degree and his PhD at Cambridge. He is considered one of the world's leading researchers in graph neural networks and also in geometric deep learning, which will be the subject of his talk today. Uh, we would like to thank the University of São Paulo and the Institute of Mathematical and Computer Sciences for their support, and Petar for and before the talk begins, we would like to give a quick note for the Portuguese-speaking audience. Boa tarde a todos. Antes de a palestra começar, eu gostaria de avisar que ela vai ser realizada totalmente em inglês. E caso vocês precisem assistir com legenda em português, vocês podem assistir o vídeo gravado algumas horas depois que ele for publicado no YouTube, depois que a live for concluída. And that was it, and we can begin the talk now.
All right. Thank you very much for the kind invitation to present to you all today. Thank you all for coming to listen to my talk on geometric deep learning. And thank you, Matteo, for the introduction. So as mentioned in the intro, we are going to be talking about geometric deep learning. And it is a topic that has been very close to my research interests over the past couple of years, and it's a topic that I believe is quite interesting and fundamental to improving our understanding of how neural networks come about in the first place, what are their foundations, how to maybe construct neural networks that might act in the best way under certain circumstances. So these are all pretty interesting questions. But when you observe the very term geometric deep learning, you might wonder what is actually the point. Like, where exactly does geometry come from? How does it relate to the spatial geometry we might be more familiar with? What does all of this have to do with deep learning, and so on? So in order to be able to answer this question in the most robust way, I need to start this talk by taking you back in time. And when I say back in time, I mean way back in time, to say 300 years BC, to the days of Euclid. I believe many of you will be familiar with Euclid's work. He is the original inventor of what we now know as Euclidean geometry. And for many, many, many centuries, the Euclidean geometry was synonymous with geometry. Like, if you were doing geometry, you were doing Euclid's original postulate geometry. And as you might know, Euclidean geometry tells us a lot about what we now know as Euclidean spaces, how different objects interact in those spaces, and it's resting on a series of postulates, the most interesting of which is the fifth postulate, which talks about parallel lines. So if you have a particular line and a point outside of it, the parallel postulate says that there can be only one line parallel to the given line that crosses that point, right? And many mathematicians believe this is a beautiful explanation of mathematics and geometry and wanted to go ahead and try to prove it, that it must be true. And usually the way in which these proofs would go is you would start by assuming the postulate to be false and then hoping to derive a contradiction. However, something truly exciting started to happen around the early 1800s mainly through the work of initially Lobachevsky and then also concurrently Bolyai. They have actually assumed the parallel postulate to be false, and they ended up discovering not a contradiction, but completely new self-consistent geometries, basically such that they did not violate any of the other axioms of geometry that we have, but they allowed you to draw more than one parallel line through a particular point. And this is now actually what we know as hyperbolic geometry. It was first discovered around those times. And this was basically the beginning of what happened to be a pretty big boom in the realm of geometry. And one particular mathematician who worked quite extensively in this space was Riemann, who, among other things, pioneered this idea of elliptic geometry, where your points, your geometry lives on a sort of surface of an ellipsoid or a sphere, where actually there are no parallel lines whatsoever. So the 1800s are basically a really, really exciting time to be doing geometry. There's all these different proposals floating around, and as a young mathematician coming into the field, you might have looked at this and wondered, what is the one true geometry? Like, what is the geometry that explains all of them, now that we have this whole zoo of them? And the solution to this particular problem, luckily we didn't have to wait long for a blueprint that offered a way out of this. We only had to wait a couple of decades. In the 1870s, one of the main reasons behind how we managed to settle this issue was this mathematician, Felix Klein, who had just accepted a professorship position at the Bavarian University of Erlangen in Germany. And as his research program, which he presented at the time to the university, this blueprint, which now we know eponymously as the Erlangen program, basically offered us a way out of this problem. It basically claimed that there isn't really a one true geometry, but there is a blueprint you can use to unify all of them and describe all of them. Essentially, the way in which it works is it explains these geometries through the study of invariances and symmetries. So it talks about not necessarily the objects themselves, but what are the quantities that those objects are invariant to. And this is something you can formalize very cleanly using group theory, which we will discuss during this talk. And this is something, as I said, that offered us a pathway to unify all the geometries known at the time, and it really had a massive impact. It's really hard to overstate the amount of impact that the Erlangen program had on mathematics and beyond. As you might expect, it did help us eventually unify all of these different geometries under a common lens. It did take some time before this was all completed and formalized, mainly through the work of Élie Cartan in the 1920s. So it really did help unify the concepts of various geometries under a common umbrella. And what also is quite impressive is that it had great spillover beyond the realm of mathematics and into the realm, for example, of physics. I hope that some of you are familiar with the work of Emmy Noether. She was actually a colleague of Felix Klein's, and she was a physicist who worked a lot on conservation laws. And actually, using the ideas from the Erlangen program, Emmy was able to show in what is now famously known as Noether's theorem that you can basically extract all of the conservation laws in physics through observing some kind of a symmetry and some kind of a group theoretic view of the physics. And what's really exciting is that this is a concept that permeates physics to this day, to the most advanced parts of physics. In fact, the Standard Model, which is our current best estimate of how elementary particles come about and interact with each other, is directly related to irreducible representations of certain groups. So it is no overstatement to say that the Erlangen program had a very considerable effect in physics. Then I trust at least some of you are computer scientists by training, and in fact, the Erlangen program also had very far-reaching effects in the realm of computer science, specifically in the domain of category theory, which is one of the most abstract branches of mathematics, which is very frequently used to describe concepts in programming languages and the similar. Through the words of the very creators of category theory, Eilenberg and MacLean, you can observe all of category theory as basically a slight generalization of Felix Klein's Erlangen program. So lots of spillover effects, not just in mathematics, but also physics and computer science. And at this point, you might start to wonder, Petar, why the hell are you telling us about all of this for the past 7 minutes? Like, I thought I've come here to listen to a talk about deep learning, and yet you're here telling me about mathematical programs, how they affect physics, how they affect computer science. So really, why the hell are we talking about all of this, and specifically about the Erlangen program? Well, now finally allow me to take you back to the present. So now we are in the 2020s. And we are doing research in deep learning. And what is happening in the field of deep learning this decade? You have a lot of different possible excitement in the field about its applications in various domains that are quite impressive. And there's also a huge family of different models being touted as possible solutions to various problems in this space. You have convolutional neural networks, recurrent neural networks, transformers, graph neural networks. And typically these architectures, they're not just kind of applied on specific problems, but a lot of them are basically tied together with some of these bombastic statements about essentially how general and applicable they are. You might see people claim things like convolutions are everything that you need, and everything can be expressed as a convolution. Everything is a graph, and you can always represent it using a graph neural network. Transformers use self-attention, and as we know, attention is all you need. Or recurrent neural networks, well, LSTM specifically, are Turing complete, so why would you ever need anything else, right? So I would actually argue that the field of deep learning in this decade is really not at all dissimilar to how mathematics was in the 1800s. We're really all searching for this one true architecture and trying to come up with convincing evidence why there is one particular architecture in a sea of different architectures that will solve all of our problems. But to be honest, if history is to teach us anything, like what happened in geometry, it never was the case that there was one true geometry, but there was a family of geometries, and there was a way to derive all of them by looking at their unifying principles. So with that in mind, we try to set out not to find the one true architecture, but to understand where the architectures come from and what unifies them. And with that in mind, now it is our turn to study geometry. The same principles that allowed Klein's Erlangen program to come about might also see their application in helping us make sense of where do all of these different deep learning architectures come from. Now, before we dive into that, though, I'd say it's very useful to raise the question of should we be doing this? So geometric deep learning is this field that studies how different deep learning architectures can come about through their geometric principles, much like how different geometries came about through their group theoretic principles. But it's really important to sort of start thinking about should we be doing this? Like, is it necessary? Is it an off-ramp? Like, is it a waste of time? In fact, I don't know if any of the people in the audience are active on the social network X, formerly Twitter. I'm quite active on it myself. There is a reasonably big and growing group of people that basically claims that group theoretic or geometric ways of looking at deep learning concepts is not necessarily something that's a useful way to spend your time, and you might end up basically having a better time if instead you just focus on scaling transformers, right? Now, I do have some arguments. I do think, by the way, I don't think that these arguments are to be discarded. I think they are very important arguments, and we need to discuss what is it that geometry brings us in this specific time and age when almost everything seems to be throwable into a transformer, right? So my particular argument that I like to give for why we should still think about geometry, even if we don't end up building architectures that are inspired by it, is because very often, at least, we want to use machine learning to understand nature better. right? We want to make better sense of what's going on around us in the world so that we can make better decisions, actionable decisions that are deployed to drive really important outcomes. For example, being able to forecast the weather better or being able to invent new medicines. And for the most direct argument here, data that comes from nature is basically often geometric, right? Very often there is a very irregular shape to it, and it doesn't immediately correspond to a nice kind of tensorial representation that you might expect to see from images or text, right? So just to give you a few examples, the molecule, which is the basic building block of life, can be very easily represented as a graph structure of atoms connected together by chemical bonds. And then you can go from there to highest levels of organization of the human body, different tissues, their interactions. Once again, data in medicine very often doesn't follow that very nice format that you might expect from text. Another great example are larger biomolecules. So the molecule I showed you on the left is quite small in comparison. When you look at things like proteins or DNA, those tend to be much bigger molecules, and they don't only have a chemical structure, but they also fold in each other in three-dimensional space. And suddenly, you get a very interesting three-dimensional structure that comes about in these molecules that if you simply represent them as text, you are basically throwing away, right? Then many interesting objects, both in abstract mathematics and other branches of science, can be represented as graphs. And also many predictions that we care about as humans will live on the surface of the Earth, right? And you cannot just flatten the surface of the Earth and run a convolutional model on it and expect the best possible outcomes, because basically you're stretching the projection around the poles, and the model will not be treating different parts of the Earth in the same way. Really, you should treat the surface of the Earth as a sort of a sphere. And this might be really important if you need to predict the weather or predict the outcomes of astrophysics measurements, which are usually projected onto the Earth's surface and stuff like that. So very often, basically, data that we need to predict things in nature are often geometrically shaped. And as a result, models, like actual machine learning models that we use to make decisions about nature, are also very often geometric. You probably know of Nature and Science. Those are the two top-tier journals of science in the world. Getting a paper on the cover, or getting a paper in these journals is already really, really hard, arguably one of the hardest things in all of science. But getting them on the front cover of these journals is even harder. And these three, I've just outlined three covers of Nature and Science, which have been powered by geometric models. So on the far left, you have AlphaFold 2, which uses a geometric model to predict how proteins fold on each other, which was at the time lauded as a solution to the protein folding problem, and recently led to a Nobel Prize being awarded to some of my colleagues at Google DeepMind. In the middle, you have our work on using AI to assist mathematicians with their intuitions and making better predictions. This is one of the earliest works where AI has successfully led to top-tier results in research mathematics. And it heavily relies on the graphical and geometrical structure of mathematical objects, such as knots and representations. And on the far right, you can see artificial intelligence being used, as I mentioned a few times, to predict the weather. One of the current state-of-the-art systems for predicting the weather, GraphCast, was on the cover of Science a couple of months ago. And basically, it also leverages a geometric model which directly represents the surface of the Earth as a sphere. So, when you actually look at what models tend to occupy the most exciting scientific applications, they tend to all very much take into account the geometry of the problem that you're solving. And this is just Nature and Science, like the highest tier journals. If I'm allowed to go just one level down to more specialist journals like Nature Physics, Nature Methods, Nature Machine Intelligence, these are all still super hard journals to get into, even harder to get covers on. basically you can find many, many covers where geometric methods are used to model interactions between proteins, the structure of glassy systems, understanding computational genomics. In fact, if we look at Nature Machine Intelligence, I could make many slides just with covers of Nature Machine Intelligence where geometric models are used to model various exciting things. So that's one argument. Like, if you want to solve problems coming from real life and truly understand and model the structure of the real life data, you might still, say, but okay, what if I just want to model language or just want to model images and I don't actually care for solving problems where I have more data than that? I think there is a good reason to study geometric deep learning, even if you are in that position yourself. You might say, there's no such geometry in language, for example. But I want to emphasize that here, especially in the spirit of Klein's work, we are not looking at geometry as just something three-dimensional or spatial. And in fact, when we talk about geometry here, we really talk about constraints, right? So we are not just saying, we have to model 3D data. It's more like our model has to behave predictably when we make a particular modification to our data. And in fact, even models like transformers, which nowadays we tend to use a lot for a variety of different problems, they're touted as generic models, but they're actually significantly constrained. You have a very specific tokenized representation of every single token in your word sequence, and your model is well aware of these token boundaries and allowing the tokens to pairwise interact with one another in this causal graph structure. There are actually a lot of geometric constraints inside a transformer, and this specific response that I wrote on X some time ago, I think illustrates this really well. Like, if you want to understand better how to, why is it important to think about symmetries and how to embed them into models, feel free to try to write a language model, which is just a MLP looking at token embeddings without any, specific permutation of those token embeddings assumed or anything like that. That has the least group theory baked into it, and probably it is not going to work. So you do need to think about constraints. You just need to choose the right level of constraint for the level of generality your application is asked to do. And this is actually what I think geometric deep learning is best for. It gives you a perspective to understand these constraints and use them to categorize architectures that already exist. And I think this is a useful perspective, like being very upfront about what is it that your architecture can and cannot do, even if you never encounter geometric data yourself, right? So in the very least, it will allow you to have a principled way of thinking about frontier models of the past, present, and future in a way that's a little bit less hand-wavy and a little bit more from first principles. Okay, so the recommended reading, I will obviously be giving you a digest version of what you can find in the geometric deep learning program. But it's all guided by our proto book, which with Michael, Joan, and Taco, we are currently writing and hopefully will come out as a proper book next year. But we have geometricdeeplearning.com, which is a very nice resource website where you can find the whole proto book, blog posts, code, an entire lecture course that we gave a couple of years back, talks and things like that, like lots of goodies that you can use to improve your understanding or maybe gain some more nuance that I won't be able to give you in the space of a single talk. Okay, so with that out of the way, it was kind of a long-winded journey about motivations, but I felt like it was important to cover that because many people think of geometric deep learning not necessarily in the way it's best used and best understood, and that's why they might discard it without actually giving it the attention it deserves. So I hope that you found this introduction useful and not too slow. I am now going to dive into how we can actually use group theory and representation theory, just like how Klein used it to model mathematics, how we can use it to model deep learning. And to do this, we are going to introduce you to groups and representations. And those are the fundamentals of capturing regularity in nature. So before we dive into the specifics of groups and symmetries, I feel like it's important to also talk about why is this so important to us, and just call out something that might be obvious, that in deep learning, we're often interested in learning functions over very high dimensional spaces. And this is commonly an intractable problem, right? Like you might know this as the curse of dimensionality problem, but generally, the more dimensions you're fitting your data in, the more samples you need in order to make it happen. And there's these very nice examples, even when your targets are well-behaved functions, like don't change too fast, like one Lipschitz or something like this. You can construct these counterexamples where the number of training points, here in red, grows exponentially with the dimension in which you're fitting your data, right? So this is something that's really tricky to do. Even if you have a function that could, in principle, approximate anything, finding those solutions from a training set with gradient descent is really tricky. Fortunately for us, we can inject some assumptions about the geometry of data through what we know as inductive biases. And what this means, it's a rigid mathematical constraint. We are restricting the functions that we allow our model to express to only the functions that respect the geometry that we care about. And this obviously results in a much smaller space of functions that we're allowed to express. And this makes the problem more tractable, even though it's in high dimensions. Here's a few popular examples of geometries you might want to embed. First of all, image data. So here's a picture of a cat. Very common assumption that leads us to convolutional neural networks is that we should be able to have more or less the same answer on a lot of these image inputs, even if we shift the input somewhat. So if I choose to slightly modify where exactly my cat is in the image, ideally my classifier should still classify that as a cat. And this might be a property I want my model to express always, like mathematically rigidly, not approximately. This is one type of geometry, the so-called shift equivariance that we can express. Then maybe for something a bit more exotic, we mentioned weather prediction, which often happens over a sphere. If we have data that lives on a sphere, we can rotate that along the sphere in many different interesting ways, and it should still be treated accordingly. So for example, if I have this nice smiley face, I can rotate that smiley face along the surface of the sphere. It should still be recognized as a smiley face. Like my network should identify this as a smiley face in all three of such configurations. And this is something that leads us to rotational equivariance. Then, I personally work a lot on graph machine learning. So very often the inputs I care about will just be irregular graph structures. And there's many different ways to represent the same graph. Ideally, you want your graph neural network to give you the same answer when it's the same graph. So ideally, it should give me same outputs even when I isomorphically change my inputs. Here, as an example, I have two such graphs. It might not appear so immediately, but these two graphs are actually the same graph, okay? And yeah, essentially, these isomorphic transformations should not affect what comes out of our graph neural network. In fact, this so-called permutation symmetry is present in transformers as well. And this is what we will attempt to formalize. Now, it's going to take a few steps to get there, so I'm going to just start by outlining a roadmap for how we're going to formalize this so that like it's completely clear when and how we get to it. So first of all, in order to be talking about the geometry of data, we need to formalize where this data is. That's going to be our domain, and how to put features on the domain. That's going to give us so-called signals. Now, once we have domains and signals, we can formalize what does it mean for there to be a symmetry on that domain. So a symmetry here is some transformation we want to not affect the prediction of our model. And we can use groups to express those symmetries, as we will see. Once we have groups, we can formalize how they act on the domain. That will give us the concept of a group action. And since deep learning won't concern itself with abstract group actions, we need to concretize them into something that maps to what we have inside the computer. As you probably know, deep learning typically concerns itself with data that lives in matrices, and we just process them by doing matrix products. We need to be able to talk about how can we express the group action as a matrix product, and this leads us to the concept of representations. And finally, like it will take a while, but it will be worth it, I promise. Once we have representations, we can formalize then properly what does it mean for a deep learning model to respect symmetries, giving us invariance and equivariance constraints. Okay, so let's get to it. The first stuff that we have to define are domains and signals. So first of all, what is our domain, which we will often denote using omega. And here on the right-hand side, you have an example for an image. So the domain is really just the collection of points on which we are storing data. For example, in an image, that might be the set of pixels. So in the case of a 2D image that's n by n, our omega will literally just be an n by n grid, or Zn times Zn, right? So this literally gives us the space of all possible coordinates on which we might want to plant data. More abstractly, if our input is a graph structure or a set of tokens, you might just have an abstract set of nodes without necessarily a structure like a grid has, right? So that's where our data lives. That's the omega. Now, in deep learning, we typically want to featureize all parts of this omega to be used as inputs to a model. And for that, we define a vector space C, which we call our channel space. So that is the what we put in every single element of omega. Once again, in the example of images, this might be r to the 3. So it's 3 real numbers telling you what is the red channel, the green channel, and the blue channel of that particular pixel of the image. And what is then a signal? A signal is just a mapping from elements of omega to elements of C. So a signal is one particular featureization of our domain. And we can talk about the space of all possible signals on omega, which we will often, for short, just denote x of omega. It's the collection of all possible features that you might put on omega. And one thing that's very convenient for us, because we deal with linear algebra, is that very often we will deal with discrete finite omegas. So there will be a finite number of points that we have to featureize. And those we can always express using linear algebra, using matrices. So we can often talk about signals not as functions, but as matrices, where every row of the matrix is one element of the domain, and every column corresponds to the dimensions of our feature space, right? So the ith row of that matrix gives us the features of the ith node in omega, right? So that is the main framework that we are working with here. Okay. Now, it's going to be useful for us to be able to do interesting things with the space of signals. And specifically, one such operation that we will often assume is possible is that we can add signals together or multiply them by scalars, and those will transform in the usual way. So for example, we can have these two different pictures of bugs, and we can talk about the sum of those two signals as just, you know, the addition of the pixel intensities in those two different places. And what this means is that the space of all signals is a vector space. And it's actually also possible, if you do a bit more work, to define an entire inner product of two signals, as long as you have a well-defined inner product on your feature space and a measure on your domain, which actually also means not only is the space of signals a vector space, it's also a Hilbert space. This is not something that's going to be important for the contents of this particular talk, but if you want to dive into how to define neural networks over spheres, it starts to become really important, because you have to talk about what would a convolution even look like over the sphere. Okay, so that is the key stuff. We've talked about the domain. That's where we plant our data. We've talked about the signals. That's the actual featureization of the domain. And now we are ready to talk about the key player that we want to embed in our models, and that is the symmetry. So maybe it's good to start with an informal definition. So a symmetry, broadly speaking, is any transformation of an object that, for all intents and purposes, leaves it unchanged. Now, what exactly is unchanged is a bit in the eye of the beholder, but it's a very clear assumption that we are making. And I find this is best to visualize on a particular example. So here is one very simple initial example that you can get. Here, let's look at the domain of triangles. So our omega here are 3 points in the 3 corners of the triangle, and we might featureize them with particular signals like 1, 2, and 3. And there are certain transformations that we can make to this triangle, which fundamentally still leave it as the same triangle. It's just being observed from a different perspective. And such transformations are 120-degree rotations and horizontal flips, right? And using these two, I can describe a collection of transformations which through which I can, in various ways, compose how my triangle can change and still effectively stay the same. And we might want to build a triangle neural network that is resistant to these changes and gives us the same response in different cases. Now, note that the very act of saying this transformation leaves the object unchanged immediately draws with it certain mathematical properties. Okay, it means, for example, that the identity transformation, which does nothing to the object, must be a symmetry. If I have two symmetries, A and B, I can compose them, and the result should still be a symmetry. And also, every single symmetry transformation, because it doesn't change the object, I should be able to go backwards. I should be able to invert it. You take all of these different properties together, and you actually end up recovering a standard mathematical object, which is known as the group. Now, I trust some of you might be already familiar with the concept of a group. If you need a refresher or you haven't heard about it before, this is what a group is abstractly. And I've outlined all of the different axioms. So a group is just a collection of objects with some binary operation, usually called composition. And that composition has to satisfy certain properties like associativity. There must exist an identity, there must exist an inverse, and there must exist closure. So for every pair of objects in the group, their composition must also be in the group. And once again, I like to show visual examples of cute symmetry groups. And on the right-hand side here, you can see my personal favorite symmetry group, which is the Rubik's Cube group of symmetries. Okay. Now, the key thing to note here is that this is a great language for specifying transformations that we are going to care about, but essentially, this is still just an abstract collection of objects. Okay, like it's not. It is not telling us yet how it transforms data. In order to get to that point, we need to add a bit more structure on top of the group. So while what we want to describe, right, are these transformations that take points in omega to different points in omega, therefore modifying our data space, the abstract group is just a set of elements with a composition rule, right? And it doesn't tell you how to transform data. In order to do that, you need to define something called a group action. It's often quite simple to define, but in essence, it is a map which takes a group element and takes an element of your domain and maps it somewhere else on the domain. This has to satisfy certain axioms. For example, if I act with identity on a point in the domain, it stays where it is. And if I choose to act with one transformation, then with another, it should be the same effect as if I first composed them and then acted once on my input point. So as long as those axioms are satisfied, this is a valid group action. And once again, this is best concretized on a visual example. So let's imagine, for example, that my group are two-dimensional Euclidean motions, so a rotation plus a translation. And these can be expressed, I hope you agree with me, using three real numbers. So the first real number tells you the angle by which you're rotating, and the other two tell you the vector with which you're translating. And those three numbers, the element of our G, act on a point in 2D space by following the usual roto translation rule, right? If you want to verify that this makes sense, it might be good to take this transformation and verify that it satisfies the axioms of a group action. Okay, now what I've just told you is how the group actions act on omega. But what we might actually care about is how they act on data, the x of omega, right? The signals. And luckily for us, the way in which we have defined our signals always gives us an action of g on x of omega that we can leverage. Specifically, this is the golden equation that's worth remembering. So if I want to act with a group action on a signal, and then I want to look up the result in some point u, that is the same as looking up the original signal in u inverse transformed by g. Now, this might sound a little bit weird at first, might take a little bit of time to digest where the hell does this inverse come from. But I feel like, once again, it's easy to maybe visualize it, for example, with this rotation of the sphere, right? So this G rotates the sphere along with this signal that's on the surface of the sphere. There's different colors. And what you're doing with the right-hand side of this equation, right, is you're hunting for the point that will end up in U's place once you apply G, right? And that is, by definition, G to the -1 of U, because the G and G -1 will cancel each other out, right? You're looking for the point in your signal that will end up in U's place once you apply G. Think about it for a little bit. Try to internalize it on the example of the sphere. I think it's a really important transformation to keep in mind. So if we have G acting on U, we can use that to get a G acting on X. That is basically the idea. And as long as our signals are part of a vector space, then this particular type of a group action on signals is linear. And what does this linearity mean? If we have two different signals that we are composing by summing them, it actually doesn't matter if we first sum the signals and then transform, or first transform two signals individually and then sum them. We'll get exactly the same results. So here for these two pictures of bugs, which we want to sum and then shift, it doesn't matter if we first sum and shift or first shift and sum, the final result is the same. And with our current definitions, this actually holds. And this is great news for us because in deep learning, we care about linear algebra, right? And that means we're also going to be able eventually to talk about these group actions as matrix multiplications. And that's great. This is what deep learning is all about. And in order to make this very concrete, for now, we will assume that we have a discrete and finite omega, as is often the case in deep learning. And that means we can always assume that our features on the domain are representable using this matrix capital X that I showed you before. So it has number of rows equal to the number of domain elements and number of columns equal to the number of features. Now, in this particular setting, we can now finally talk about what does it mean for a group action to be expressible using matrix operations. And that is what brings us to this concept of a real representation of a group on a particular vector space. It's this map here, rho, which takes a group element and gives you a matrix. And this matrix is the thing that, when it's multiplied with your data, ends up applying the group action to that data. Okay, so what it does is it assigns to each group element an invertible matrix that satisfies the rule you see at the bottom here. So if I have two different group actions, I can either first compose them and then extract the matrix corresponding to them, or get the matrix corresponding to the first one and the second one, and then multiply the two matrices. As long as this is satisfied, this is a matrix way of representing what my group actions are doing. Once again, this is best visualized using concrete examples, which I will show you in a second. But a few things that are important to note is that this representation, rho of X, does not need to put different matrices to different elements of G. If it does, it's called faithful, but there can be many transformations, representations that we care about that actually will have different elements of G act in exactly the same way on the data. And it's interesting to think when that might happen. So here is a concrete example where my data lives on a one-dimensional sequence. This is quite common nowadays with text. And I want to talk about transformations that cyclically rotate our sequence. So here our group is 1D circular shifts, which I can represent using natural numbers, integers Z. And our domain has, say, 5 elements, so it's Z5. And the action of Z on Z5 here is really just to add that particular shift and mod by 5, right? This is something we can express using a matrix product, specifically using this matrix over here. This is a circular shift matrix. You might be familiar with this from signal processing. The only effect that this matrix has when you raise it to the power of n is it shifts your signal circularly n steps, right? So that's this row, like, basically takes every possible shift and gives you a matrix corresponding to that shift, so that when you multiply your data with that matrix, it just shifts the data. It can be a fun exercise. It's a bit more involved, but useful to verify your understanding, to check that you can derive the representations for also the 90-degree rotation group and 3x3 grids. Okay. So now finally, it's taken us a while, but I hope you'll agree with me it was worth it. We can talk about how to use all that we have learned to formally describe what does it mean for a neural network to respect the symmetries in a group. And the first such concept we will describe is invariance. So we say that our function, so let's say we have a function, a neural network, that takes as input some signal on a domain, so some data, and outputs some output. For example, it classifies the input in different classes. And we say that that function is G invariant if no matter what group representation I apply to my input, it doesn't change the output, right? So the output is unaffected by the group action on the input. This is best visualized in the case of image classification. Arguably, convolution networks are often built to be shift invariant. So here G is the shift group. And here is one particular classifier which predicts what bug is in the image. It has the shift invariance property, meaning that if I shift where my bug is in the image, my classifier has to answer the same way. It has to predict the bug class of this particular type. Now, it's interesting to study what does this invariance constraint do to a model and its specific representations. To study this, we will introduce a concept of an orbit. Specifically, you might think, because as we discussed, right, every single element, when you start transforming it with a group, eventually you'll be able to go back where you came from. So you can describe basically these different islands that all correspond to the same item. Here, I've chosen a very easy group to reason about this. It's a group of 90-degree rotations. So there's exactly 4 possible orientations that every single input image can have. And it basically cuts all of the possible inputs I can have into these islands around a particular point. And we call these islands orbits. So an orbit around a particular item is just the collection of all the inputs that you can get by applying group operations on it. And an invariant model can enforce that everything that's on the same orbit will be classified in the same way, which can be a really useful constraint when you don't have enough data points. And actually, it's easy to check that these orbits then specify an equivalence relation. For those who do not remember, for an equivalence relation, you need to show it's reflexive, transitive, and symmetric. And this is something that might be useful to verify if you have a bit of time after this talk. But the key thing is, when you have an invariant model, it will reduce all of these orbits to a unified representation, right? It forces everything on an orbit to be represented in the same way, so that then a classifier doesn't have to deal with the nuances of 90-degree rotations. It is forced to predict things differently for these 4 inputs. Now, invariance is a really cool property, but it also comes with certain problems, right? Specifically, it's great when you need one output on the entire domain, but what if instead you need to predict stuff for every domain element separately, right? And also sometimes, even if you just need to predict one thing, like basically, sometimes you might rely on essentially the nuance that equivariance can bring you, right? So sometimes, even though you only predict one thing for the whole input, if your representations are invariant in the wrong way, you might lose critical information. So here is a simple example on these inputs like smiley faces. If you have a rotation invariant model, okay, it will be resistant to you rotating all the individual parts. That's still a smiley face. But it might also erroneously have invariance to you only rotating certain parts of the smiley face and not all of them. And as a result, you might end up mispredicting that input on the right if you're overly invariant. So that relative pose of objects is sometimes very critical. And this is something that Jeff Hinton has been talking about for a long time. There was an ICANN paper in 2011 that talks about it, for example. So because of this, we actually proceed to define a more fine-grained notion of regularity. And that is the concept of equivariance, okay? So basically, you have a function that now maps signals on omega to different signals on omega. So now we are predicting things on different parts of our domain rather than reducing them to just a single class. And we say that this function is equivariant if no matter what group action I choose, it doesn't matter if I transform the input or the output of the function, it will affect the procedure in exactly the same way, okay? And one example of this, which is pretty quite beautiful, I don't know if you can easily see the animation, but it is image segmentation. So here is the case where you don't need to classify an entire image. You need to classify every pixel in that image for what is the object there. This is commonly used, for example, in road network inputs or medical imaging inputs. You often need to make sense of what's happening in different parts of the image at once. And here, we don't talk about shift invariance because we're not predicting things in every single in the whole image for just one output. We are predicting an output everywhere. So if we shift an image, naturally it needs to change our predictions, but it must change them in a predictable way, right? So we have this shift equivariance property, which is baked into convolution networks, that says that when you shift this input, for example, in this vertical edge detector, as you shift the object, the predicted boundaries move together with the object. And this is not approximate. This is something that is baked into the architecture of the image segmentation model. One thing that's interesting to note here is that invariance is actually a special case of equivariance. And I'll leave it as an exercise for you to figure out under which Z representation do you end up recovering equivariance. End up recovering invariance from equivariance. Now, it's good to think, we talked a little bit about orbits and what does invariance do to representations. We can also talk about what does equivariance do to representations. I've left the equation of equivariance in the lower right corner just to make things a little bit easier. So let's imagine I have these two different A characters in my input space, and I'm denoting them as X and Y. And let's assume that we have a function that maps both of them to the same representation. For example, we need to classify both of those as an A character, or we need to represent abstractly both of those as an A character. And let's assume we have found a function that does this. Now let's assume that I rotate both of these inputs along an orbit. And let's assume my model is equivariant to that orbit. What does equivariance tell us about the representations of these two letters? Actually, it tells us something very specific. It tells us that you cannot represent these two A's differently, right? This is the key thing that's more fine-grained about equivariance. The constraint there is that you must generalize in a consistent manner across the entire orbit because you have equivariance. So if a model is equivariant and two different inputs map to the same representation, then their transformed inputs must also map to the same representation. But now, because it's not invariant but equivariant, those representations of A and rotated A don't have to be different, right? There has to be some kind of transformation mapping from one to the other, but that one is now predictable. And unlike invariance, these two can be different. So the A and rotated A don't have to be the same. So these are the key points in building functions that are resistant to certain types of symmetries. And as a result, we can now describe the building blocks of geometric deep learning. I've outlined all of them here. This is basically a direct copy from the book. You don't have to dive deep into them. It's useful to consult later as a reference. I'll just highlight the key parts to focus on. So we've mentioned equivariance. We can build equivariant layers. You might notice I'm saying to make them linear. I'll describe why in a second. And also, so these are great if you want equivariant predictions in your model. And sometimes you actually want invariant predictions. And for those purposes, we have invariant layers, sometimes also called global pooling layers. Now, why did I say that it's sufficient for us to look at linear equivariance? Well, first of all, because linear equivariants are much easier to find in mathematics generally than nonlinear ones. And in deep learning, we have a very nice cheat code that allows us to build nonlinearities in a model by just having activation functions applied to every part of our input, like ReLU or sigmoid functions or something. And then if you compose those nonlinearities with the linear equivariant maps, we basically end up with essentially in most cases, we can prove that this is sufficient to represent any function that we might care about over those inputs that has the right symmetries. We also sometimes might want to not completely pool our input, but pool it somewhat to get a locally coarsened input. And for this, we can also talk about pooling layers that map signals on omega to signals on a slightly smaller omega prime, although we won't talk about this in great detail today. So Altogether, you get a blueprint that looks something like this. I've used graphs here as input because they're a quite general domain. So we basically stack a bunch of equivariant layers, apply local pooling if we need to, more equivariant layers, and then in the end, if we want to predict something over the whole domain rather than parts of it, we have this global pooling layer at the end. And the way in which we achieve the nonlinearity and universality of these models is by plugging in nonlinearities like ReLUs or something like this in between every single linear equivariant layer. And this is a remarkably powerful blueprint, it turns out. Much like how Klein's Erlangen program allowed us to use equivariance and invariance to describe different geometries, we can use them here to describe many different deep learning architectures. In fact, we talk about this at great length in our proto book. You just choose the right domain that your data lives on, the right symmetry group that it's applied to, and you get basically different architectures. We already discussed how convolutional neural networks arise as a result of translation symmetry on grids. And in fact, you can find that convolutions are exactly, this is a known fact in signal processing, they're exactly the collection of linear equivariant functions on grids. So convolutional neural nets are exactly the model that is translation symmetric on grids, and no other model can be. We can also discover things like deep sets, transformers, LSTMs using different settings. What might be interesting is that also it allows us to talk about these more exotic domains like spheres or even manifolds and meshes. So what I want to do in the remaining part of the talk is just show you this on a concrete example. Right? We're going to talk about permutation, equivariance, and invariance, and how it allows us to rediscover models like deep sets and graph neural networks. And that is going to be where we conclude. So we're going to start by studying sets, which you can think of as graphs without connections. There's a good reason why even in the book we start this way. It's because sets are arguably the simplest domain to analyze. There's no inherent geometry attached to them other than there's a collection of points. Many conclusions you find on sets will very naturally carry over to graphs. And even if you just stay in the domain of sets, those can be still quite relevant, because for those of you doing computer vision or self-driving cars, you might know about point cloud data or LiDAR data. Self-driving vehicles like this Waymo demo on the right, they often have to make sense of what's happening around them, basically through a collection of points that they get from LiDAR sensors, right? So basically, it's still really relevant, even if you only limit yourself to collection of points. So let's assume we have a graph with no edges. Our domain omega is just a set of nodes. And let's featureize each node with a feature vector xu. As we discussed before, because the domain is discrete, we can express this signal by just a stack of node features, such that a particular row of that matrix corresponds to features of a particular node. Note that the very act of doing this is potentially bad, and you shouldn't be doing this, because the very act of stacking your features into a matrix specifies an ordering of the nodes. And you might want your result of your set neural network to not depend on that, because you haven't defined any particular order of your nodes. So what do we want, really? Let's imagine I have this set of objects with different feature vectors. And let's imagine I have like a set classifier that takes these node features and predicts some output. What I want is for this model to give me the same answer, even if I choose to perturb the exact way in which I present these 5 objects to it, right? And it turns out that we can talk about these operations that change the node order very rigidly in mathematics. Those operations are known as permutations. As you probably know, for n objects, there are n factorial many permutations. And in fact, they form a symmetry group, which is the n element permutation group. And their group elements are individual permutations. And as we discussed, we can express a representation of this group. Each permutation uniquely defines an invertible matrix, which is known as a permutation matrix. Here you can see what it looks like for the permutation 2, 4, 1, 3. These matrices are very special. Most of their values are zeros, with the exception of a handful of ones, 1 in every row and 1 in every column. And the only effect those matrices have is that when you left multiply them with the input, it permutes the rows, but does nothing else, exactly as we would expect. And we can then use this to describe an invariance constraint. So we can say our function is permutation invariant if no matter what permutation matrix I choose, it doesn't change the result. And of course, this only gives you a constraint. It doesn't tell you what such an f would look like. And one very popular way to express such an f is using the deep sets model. In fact, this model has been studied well before the deep sets paper, but nowadays we call this architecture deep sets in honor of the paper from Manzel, Zahir, and others at NeurIPS 2017, because it proved a lot of nice theoretical properties about these models. So how does it work? You take basically a shared learnable function applied to every single set element separately. Then you sum up the resulting embeddings, and you use another network to then, if you need to, predict stuff over the whole set. And what's critical, what gives it the permutation invariance property, is the summation. So the fact that you are summing over all of the different elements, sum does not give you a different answer if you permute the order in which the set elements are given. And this also means that you don't have to use sum. You can use something which doesn't sum but has other ways of invariantly aggregating, like taking the maximum or taking the average. For this reason, whenever I talk about these permutation invariant aggregators, I typically use this symbol O+. So that's the symbol that we use in the book to denote any permutation invariant operator. Now, recall as before, this is great if you want to get outputs on the level of entire sets. But what if instead you want to predict things in the nodes, or more fine-grained intermediate representations which invariance and summing would destroy? So we might instead seek equivariance, functions that don't change the order of the nodes. So if you have a permutation, it doesn't matter if you apply it before or after you apply your function. This gives you permutation equivariance. Note that now I'm denoting my function not with lowercase f, but with uppercase f, to denote that the output will probably still be a node feature matrix, so that I can apply this permutation to it. And equivariance and invariance are great to represent all legal functions over such an input, but it's not enough, because inputs can be transformed in many ways, and nature might transform them in many ways, and not all of those transformations will come from this group that you've chosen to study. This is once again well explained in the domain of images. So here I have this picture of a house. I might build a convolutional network to be resistant to shifts. So if I shift my picture of a house, it's still the same picture of a house. That's great. The model will process them in the same way. But nature or cameras might decide to apply different transformations to my picture and distort it in a variety of ways. Now, these distortions might still be group operations, but it's from a different group, one that I did not anticipate when I built my convolutional model. And if I'm not careful, even if my function is shift invariant or equivariant, it will still behave very badly when I give it these distorted images, right? So we want stability under these deformations of the domain. And I can't get into a lot of detail now. There's not enough time to talk about the maths behind what to do in this case. But the TLDR is, it turns out to be a really good idea to have local operations and compose them to model larger scale stuff, because the locality of these operations will not globally propagate any errors. This is basically the motivation behind why convolutional networks in practice will have very small 3x3 kernels, for example, but then you make them very deep to propagate that information more broadly. Accordingly, we would like to have some locality in our layers beyond just invariance and equivariance. What does locality even mean for sets? There is one very easy way to enforce locality in sets, and that is to just apply a shared function to every single set element and don't even consider their interactions. So you just apply a shared psi to every single element of X, and then this gives you a new feature space for each node. You stack those into the same matrix, and this gives you the output of your permutation equivariant local function. And if you look back to the deep sets equation I showed you before, you can find that this local function is exactly the first stage of deep sets, right? You start with this local equivariant function on each element separately, and then if you need to predict something over the whole set, you add this extra red part, the tail, which adds up all the embeddings together and then predicts, right? This follows the GDL blueprint directly, right? Because we have the equivariant part, which is the psi, and then we attach the invariant part to the end if we need it. One interesting point here to note is that this is actually as far as we can get with sets. Like, there are proofs both in the Zahir et al. Paper and also the follow-up work from Wagstaff, Fuchs, and Engelka, which prove that all the functions on sets that you care about can be expressed in this way, right? You might wonder, hang on, but what if I model pairs of objects or all their interactions together in psi? You can do that, but at that point, you're no longer working on a set, because every time you add two objects together in such a function, you're assuming they're connected, and you're actually secretly working on a graph, not on a set. So that's a good way. That's a good instruction to transition us from sets to graphs. So now we don't just have our domain be the set of nodes, we also have a set of edges between them. And there's many ways in which we can choose to represent those edges, but one traditional way is the adjacency matrix. Because we talk about linear algebra, it's the most kind of natural way to talk about it. I know there are many more efficient ways to represent edges, especially for sparse graphs, but we're kind of keeping this abstract here. And you can basically represent this as a binary matrix where it's of shape nodes by nodes, and the one entries tell you where the edges are in your graph. You can also put other stuff in this matrix, like edge features, edge types. They're all possible. They don't change the math, but I'm deliberately ignoring them because the math will be much simpler if I assume it's just this. And you might wonder, what's changed? Actually, I would argue not much has changed, and all the things we care about, like the permutation, invariance, and equivariance, are still very much important in this particular domain. So if you remember this picture I showed you before for set neural networks, for graph neural networks, it's actually exactly the same picture. The only difference is that now I also have some edges between my nodes, and I need to be careful that whenever I'm permuting my nodes, I need to also accordingly permute my edges, right? So all the functions we had before for invariance and equivariance still look the same. The main difference is that now I must take into account the adjacency matrix, so I must take into account the edges. And whenever I permute my nodes, I need to also permute my edges. And since we mentioned that the adjacency matrix is of shape nodes times nodes, I need to permute its rows and its columns. So that translates into PAP transposed. So the first multiplication permutes the rows, the second multiplication permutes the columns. Note that in order to allow me to just apply P to the output of the equivariant F, I need to assume that this F doesn't change the adjacency matrix and it just returns the new node features. This is a very common assumption, which sometimes isn't done these days, but just to simplify the maths, I'm assuming this is the case. Now, the part where, so the invariance and equivariance are actually more or less the same on sets and on graphs. The main part that where it starts to become different is the locality. In sets, the only way we could do locality is by transforming every node by itself, right? But when you look at graphs, you suddenly have a more broader way to express what is local, and that is a node's neighborhood. So one way to define a neighborhood is just this NU, which is the collection of all the nodes adjacent to U by an edge. And then you can use that to extract the set of the multi-set of neighborhood features, the XNU. That's just the multi-set of all the features in node U's neighborhood. And now your local function doesn't just have to look at one node. It can also look at all the multi-set of features in its neighborhood. And once you have a local function like that, you apply it to every single node's neighborhood separately. You stack the results. And, well, because this local function now depends on the multi-set of neighborhood features, the output is sensitive to how you choose to present those neighbors. So as long as the function f is permutation invariant on the neighborhood, this whole function capital F will be permutation equivariant in the permutations of the graph. This is a relatively simple algebraic result, but I would highly encourage you to try to prove it if you want to make sure that you understand all the different concepts that we described today. But this is basically the idea. We can build a graph neural network by first learning a local function around each node's neighborhood and then just applying it in parallel to every single neighborhood on its own. Now, I understand this was potentially a very mathy approach to GNNs. There exists, and this means that F can basically be a deep sets model over each neighborhood. There exists a nice visual explanation of everything we just described. We can build graph neural networks by applying a local function to features of a node and features of all of its immediate neighbors, and this maps the inputs to a latent space, right? Then how can you use this to learn interesting function on graphs following the geometric deep learning blueprint? Let's imagine I have input graphs with feature vectors xu for node u and adjacency matrix A. My graph neural network, as we just described, will look at the local features around a particular node and based on that, update the features in some latent space H. As I said, I assume that the adjacency matrix is unchanged. There are many interesting new approaches that do change the adjacency. I'm just trying to keep the math simple here. And then what we can do with these H's, if we need to predict individual node outputs, that's a node classification task. So here we have a predictor applied to every single node in isolation. And in this case, we just have a fully equivariant function where we have a predictor applied to each node separately. We might also be interested in classifying entire graphs. So that's a graph classification setting. For example, if we want to classify molecules or predict their actions from the graph of atoms and bonds. We can definitely do this. We just have to be careful that the output doesn't depend on the order of the nodes. So we need to first attach this invariant tail, just like before, to reduce all the node features to a single embedding and then predict using our permutation invariant aggregator O+. And another interesting equivariant function you can do in graphs is predict properties of edges, or even predict whether edges exist or not. This is a very important task, which is for that reason nowadays known as link prediction. It is the foundation of all recommender systems in most social networks that you use today. Like, this is how different services on the web figure out which products to recommend you to buy, or which people you should be friends with, or which music you should listen to, or stuff like that. It's basically a big graph of users, their social interactions, the products they interact with, and you can then predict new links in that network as suggestions that you can give to the users, right? And this can be just a predictor that depends on the features of the two nodes that you're trying to link and any edge features you might have between them. And this, by the way, so this is how the geometric deep learning blueprint acts on the space of graphs. And this picture here, I think, is one of the most important pictures in deep learning, because you can explain almost all deep learning architectures as some pathway through this particular picture. And it hints at something much broader beyond just graphs, how you can then use this to describe architectures on many different domains with many different symmetries, as we discussed. And I hope that it's a start of something potentially exciting for all of us collectively, and that it will lead both to better understanding of architectures that we have now, and also better understanding of architectures we have in the future. With that in mind, it was a pleasure to speak to you all today about this. And now it's your turn to study geometry. Thank you very much.
Thank you very much, Petar, for your talk. You gave us a lot of beautiful theory, and we all learned a lot. And now, before we jump to the questions of the chat, I have a question, right? So, as everyone here probably knows, DeepMind won the Nobel Prize in Chemistry with AlphaFold. And biochemistry seems like a trending application of GDL at the moment. So I'm curious about how it exploits the symmetries of the problem using GDL.
Sure. Yeah. So AlphaFold 2, which was the architecture that got the landmark result, which eventually led to the Nobel Prize, was an architecture that very directly models rotational symmetries of frames of different parts of the amino acid sequence in a protein. So it very closely understands the structure that's happening in the atom coordinates of a protein, and it makes sure that the model is very resistant to that. So yeah, it basically very directly models symmetries to rotations and translations, along with also being permutation symmetric, which is sort of usually assumed whenever you have a graphy-like input, like a molecule. What's interesting to note is that sometimes certain equivariance conditions cease to be necessary when you add sufficient scale or sufficient assumptions. So the more recent iteration, AlphaFold 3, actually drops the explicit rotation equivariance. You no longer have this in AlphaFold 3. It doesn't necessarily give the best results for proteins, but AlphaFold 3 starts to deal with interactions between proteins and other molecules. And there, the symmetries that you have for amino acids might not necessarily apply for different types of molecules. So dropping the rotation symmetry there was pretty necessary for them. And they are actually able to enforce it by doing data augmentation, which is a bit more implicit way to enforce rotations. Like, you try kind of 50 different rotations, and you make the model kind of predict similar things on those 50, rather than forcing that every single rotation is answered correctly. So yeah, this is basically the essence of how AlphaFold 2 and also AlphaFold 3 take into account the geometry of molecules.
Okay, thanks for the opportunity of hearing that. Uh, so now on to the questions of the chat. Uh, so Fernando José is asking, the building blocks for geometric deep learning generalize those of message passing GNNs. So, what interesting ENNs are developed, or at least studied, implemented for other settings rather than graphs and GNNs?
Right. So we just discussed one, like rotational symmetric models that are very heavily used to model biomolecules. We mentioned spheres a few times. So spheres and processing spheres have been a really important part in predicting the weather. Some of the recent state-of-the-art weather prediction systems are very mindful of spherical symmetries. Very obscure areas of quantum mechanics, like lattice quantum chromodynamics, are also using SU gauge symmetries to model better their predictions. Recently, actually, we used geometric deep learning in football. You might have seen our Tactic AI paper where we worked together with Liverpool Football Club to better model outcomes in football analytics. That uses D2 symmetries to better model the reflection symmetries of the football pitch, and therefore deal with a smaller amount of data that you might have in a football club compared to, a big text data set. So there's a lot more interesting examples, but those are some that immediately come to mind.
On to the next question. How could geometric deep learning be used for deeper understanding of complex multi-dimensional spaces?
So yeah, that is another good question. Oh, I see there is a follow-up. Do you want to read it out, or should I just go ahead?
You can just go ahead.
Yeah, sure. So the question follows up by asking, to be more specific, will it be possible to connect the configuration of extra dimensions that we observe through geometric depths? I would say yes, but it is very speculative at the moment. So geometric deep learning, as we presented it, is mainly concerned with understanding architectures and their constraints. It doesn't deal that much with understanding the exact spaces that this data lives in, although I suspect this will be an entirely interesting and kind of maybe even independent area of study in the future. We are going to dedicate this a few sections in our book when it's completely finished, but yeah, it is not it is not something that is a done deal, basically.
So next, do the results passing from finite groups to other finite algebraic structures such as monoids, racks, or quandles, and to discrete infinite groups, rather crucial in low-dimensional geometry and topology?
Yeah, that's a great question. In fact, I'm very active in a field known as categorical deep learning, where we try to categorify a lot of these concepts and go from group theory to category theory. Monoids are a natural stopover on the way, and we have a paper called Asynchronous Algorithmic Alignment with Cocycles, where we generalize some of these equivariance constraints from groups to monoids to be able to express symmetries with respect to asynchronous execution of different algorithms. So that's one particular interesting application that we have studied recently. So yeah, monoids have been done. There's not much work on them, but we've done one paper, Asynchronous Algorithmic Alignment, which deals with this.
So as a follow-up to the previous question, we have the following. Developing further, which sort of descriptions have worked in GDL to approach infinite geometric and topological structures? For example, simplicial complexes. Any sort of discretization or finite sampling?
That's a great question. So Basically, there have been some works in both directions. I'll start with topological structures because that one has seen a lot of work. So simplicial complexes, and cellular sheaves have been very intensely studied in the topological deep learning community, especially through the works of Christian Bodnar. So if you look him up and look at his previous research output, you will find lots of papers that pioneer these simplicial neural networks on graphs, cell complex neural networks on graphs, and these sheaf neural networks that then go one step beyond. So basically, Chris has done a lot of work on this, and he's a really, like, his works are a really good first source of understanding those particular structures. And when it comes to infinite structures, I don't know much general work, but I know of one really nice paper that was published at NeurIPS a couple of years back, which deals with equivariant networks for crystal structures. So for those of you who don't know, crystals are basically structures that keep repeating. So there is one molecular kind of pattern that then repeatedly is repeated to obtain the final crystal structure. And basically in this paper, they use this idea of a wallpaper style tiling group to reduce the prediction over the whole tiled molecule to just predicting things in a careful way with the right weight sharing over the main pattern that is being repeated.
So next question from George. Do graph attention networks using the edge feature just concatenating to create the attention coefficient make sense? What if we are dealing with the problem that is more edge centered than node centered?
Okay, that is a pretty interesting question. I would say it makes sense in certain situations. If you're dealing with problems that are more edge-centered, you could treat your edges as nodes and then use a GAT style mechanism to do this. This is, by the way, something that has already been attempted really successfully in a model called Token GT, which basically is a graph transformer where you tokenize both the nodes and the edges. What this is secretly doing is attention of edges to nodes, nodes to nodes, and edges to edges all happening at once. And it works really magically for small molecule inputs. I must stress that this also incurs a quartic complexity in the worst case, so n to the 4, which means it only really works for smaller scale inputs. But if your inputs are small scale enough, it indeed tends to work really, really nicely.
So that was it for today's talk. Thank you very much, Petar. And we will see you later, everyone, in the next talks of understanding deep learning. So thanks, everyone.
Thank you all so much.
Thank you, Petar. Bye-bye.